Verification and validation can be thought of as a formal process for checking results. Each of these terms has its own meaning. And to see that, if I go to the framework of what's inside the black box, and I've talked about this in other contexts, it might be familiar to some of you, verification is looking at, did I solve the model right? I.e., whatever mathematical model I picked, have I solved it correctly? Have I input the right mathematical model into the tool? We'll assume that ANSYS doesn't have coding errors, at least for this problem. And are the numerical errors acceptable? Okay, so verification is looking at whether you did this aspect of the problem right. Validation is looking at, did I solve the right model? I.e., whatever mathematical model I picked, is that an accurate enough representation of the physical problem? And that's where you use experimental data. And there are two kinds of experimental data, and perhaps even more. One is you can go to textbooks such as Hasluck and Armstrong, and you will find a correlation of experimental data on stress concentration factors. So you'll see like KT versus A over W, and you'll see a curve like that. And that's a stress concentration factor that comes from other people's experiments. So you can use that to validate the ANSYS model. And now there is this technique called digital image correlation that is basically a method by which you can track points on the plate using cameras and construct a displacement field, and from that strains, and you can ask the internet about more to find out more about that. So that also can be used for validation. There are lots of things you can do for verification. I'll show you two things. One is to check if the reactions balance the applied load, and the other is to check the numerical error by doing a mesh refinement. Let's first check the reactions. So I'll go into ANSYS here. Now, any displacement boundary condition, I can find the corresponding reaction. I won't get into how it's calculated. You can take a look at the big ideas in finite element analysis. It is ultimately coming from the nodal displacements. So I will find the reaction corresponding to the left boundary condition. By the way, I realized I should call this V equal to 0 at the bottom boundary. My bad. So I'll drag this to the solution, and you see it'll give you the corresponding reaction. And I'll say evaluate all results. And it tells me that the reaction is 50,000 pounds in the x direction, and the y direction it's 0, which is what we expect. There's no applied load in the y direction. Now that should balance this load. And what ANSYS does is it gets a reaction per unit thickness and multiplies by the thickness. So you have to get the thickness right just for this post-processing entity. So I'll go here and set the right thickness. And it hasn't changed the mathematical model, though ANSYS thinks it has. So I'll resolve it. And now I should see that 10,000 pounds should be equal to the force. The minus 10,000 should balance that 10,000 pound force applied at the right edge. Okay. And similarly, you can do it for this boundary condition. And that just means that, the forces balance in aggregate. It doesn't mean that the forces are balanced for each element. You could still, your stress concentration factors could still be off. So it's necessary for the reactions to balance the applied load, but it's not sufficient. And the next thing I'm going to show you is how to do a mesh refinement.